The title of the talk is Intermittency phenomenon in the self-intersection local times for Wiener process. Please.
Thank you. Thank you very much for this opportunity to give this talk in this seminar. It is in fact a joint work with Professor Andre, and as you have just mentioned, it is about intermittency in the Ito-Wiener expansion of the self-intersection local times of the Brownian motion. And before I come to this concept of intermittency, let me just recall some aspects of the self-intersection local times of the Brownian motion. It's in fact an interesting subject which kept many people busy for quite a long time, not just mathematicians, but even in other fields, and mainly fields related to the study of polymers. Polymers are, in fact, long chains of molecules, of small molecules, and these small molecules are called monomers, and these big molecules appears in many aspects, even in our daily life. In fact, many plastic devices are constructed from polymers, and there are also natural polymers like ADN or proteins and many other examples. How this self-intersection appears in the study of polymers, it was proposed, in fact, by Edwards in 1965, in 1966, to use the Brownian motion as a mathematical model for polymers. In fact, the shape of polymers are very similar to the trajectories of the Brownian motion in 2 or 3 dimensions. And so it was proposed to use the Brownian motion as a mathematical model, and this model, in fact, proved to be successful in to determine and explore the properties of polymers. However, and as it is always the case, there are some difficulties that arise, and for the polymers, there is a law called the excluded volume effect, which prevents the polymer from intersecting itself, which means this molecule cannot intersect itself, different monomers cannot occupy the same space or the same point. This is due to the interaction that exists between different monomers, and mainly the existence of repulsive forces between them. So this excluded volume effect does not tolerate the existence of self-intersection for polymers. However, the Brownian motion do have self-intersection. In fact, it was proved by Dvoretsky, Erdos, and Kakutani in a series of papers in the 1950s, that in the planar case, the planar Brownian motion do have points of self-intersection of any multiplicity. And this is almost surely on any other time interval. There are even points of multiplicity, of infinite multiplicity, and there are even points of multiplicity equal to the power of a continuum. And the situation in three-dimensional case is strangely different. In fact, there are only points of self-intersection of multiplicity 2. This is almost surely on any time matter. And in dimension greater or equal than 4, it happens that there are no points of self-intersection. And this is almost surely on any time matter. So for different dimensions, the situation is different. But in dimension 2 and 3, there are these points of self-intersection. So in the Edwards model, there is this problem of the appearance of self-intersection, and it was proposed to tackle down this problem to associate a penalty to each trajectory of the Brownian motion. So whenever we have to compute some energy or some quantity related to the polymer, and the polymer is represented by a Brownian motion path, we have to multiply by the following function, the exponent of minus beta, the double integral from 0 to t, delta 0 of bt minus bs ds dt. B here is the Brownian motion, and this integral is a formal expression which is intended to compute the time s and t such that bs equal to bt. So whenever there is a self-intersection, this function will compute the time spent in this point. Beta is a constant, is a strictly positive constant. It is called the repulsion constant, and it is takes into consideration the repulsion that exists between different monomers. So all this exponent here is, we see that if this integral is takes a high value, which means that the Brownian motion spends a lot of time in this in some point of self-intersection, then this exponent is intended to weaken this value of this high time, because we have exponent of minus something which is big. So this is a way to reduce the effect of self-intersection. But of course, this integral here with the delta 0 is just formal, and we should give it the right meaning. And there are at least 2 different ways to do this. And the first approach, we can just, oh, I'm sorry. Okay. Okay. I'm sorry. As the first approach to define this this integral, if we take a Wt to be the Brownian motion, d-dimensional Brownian motion, and we denote by delta 2 the set of times s and t, such s is smaller than t, then we can define the vegetation measure. And the following vegetation measure, mu2 of a is the integral of delta 2 of indicator of a of wt minus ws ds dt for any Borel subset a. So here we just compute, this integral is intended to compute the time spent by wt minus ws in the set A. And if this measure is almost surely absolutely continuous with respect to the Lebesgue measure in RD, then the density, the associated density is called by √2 of U, and this density can give us now a meaning of the formal expression that we have just seen. It follows from this definition that we can characterize this density √2 by the following occupation formula. It is like a transfer formula. If we integrate over the time any function from Wt minus Ws, then it is equal to the integral over the space Rd of Fu with respect to the visitation measure, and here it will be √2 of U du. This is for every positive and measurable function or bounded and measurable function f. And from this occupation formula, we can deduce in a particular case, when we take f to be this family of this is the Gaussian approximation of the unit, approximation of the delta zero function. If we take f to be this function, then we can see that we can deduce that the integral of a delta 2 of p epsilon d Wt minus Ws minus x ds dt will be by the occupation formula equal to the integral over Rd p epsilon d of u minus x √2 of u. If √2 is continuous at some point x, then this is by the properties of this family of functions, this will converge when epsilon goes to 0 to √2 of x. So this is another way. If we want to obtain √2 of x, we can just take this approximation. We see what limit does it have. This is another way to define this density √2 of x. Just when the point x is 0, and if √2 is continuous at the point 0, then √2 of 0 is called double intersection local time of the Brownian motion. In fact, the value at 0 gives us how much time spent by the Brownian motion in its points of self-intersection of multiplicity 2. So we can call it the double intersection local times of the Brownian motion. Until now, these are just definition, and it was proved by Rosen in 83 that in the planar and the three-dimensional case, the visitation measure μ2 has a density. It has a square integrable density √2, which is continuous in the space, but not at the point 0. Also, in higher dimension, in dimension greater or equal than 4, the visitation measure, this is a quite different situation, does not have density. The situation depends on the dimension. It is quite similar in 2 and 3, and in higher dimension, it is the measure does not have at all the density. And it happens that this √2 is not just discontinuous at the point 0, but it even blows up. It goes to infinity at this point 0. And this was checked by different mathematicians. For the planar Brownian motion, Varadan showed in 69, and then the same result was proven by Legal by different means. That the planar Brownian motion, if we take the density √2 of u and we just subtract 1 over pi, the logarithm of 1 over the norm of u, which is in fact an equivalent expression to the expectation of √2 of u. If we just remove this term, then we can get a finite limit almost surely and in L2. In three-dimensional case, quite similar property also appears. Root 2 of u always goes to infinity when u goes to 0. But if we subtract 1 over 2 pi the norm of u, and this is also here, this is an equivalent expression for the expectation. If we just subtract this expression, still the result goes to infinity, and we have to divide it by this square root of this logarithm to obtain a finite limit. So these renormalization procedures were proved and gave a solution to obtain a finite limit at the point 0. And they are describing also the speed of convergence of this density rho 2 to infinity. Here we can see that it is of the size of the logarithm of 1 over the norm of u, but here it is quite different. In the same context, in a paper published in 1995 by M. Keller, Pires, April, and Vips, this density rho 2 in dimension 2 and 3 was considered in a different way through the Ito-Wiener expansion. They obtained the exact Ito-Wiener expansion, and it is the following. So rho 2 of u is the sum from k equal to 0 to infinity. And here we have the sum of all the integers n1, n2, and d of sum equal to k. This integral over time, ds dt. And here we have a product of Hermite polynomials on the wj of d minus wj of s divided by the square root of d minus s. Of course, w is w1, w2, wd, and u, this point u from Rt is equal to u1, u2, and del ud. So there are these Hermite polynomials, and here the Gaussian density p in dimension d of mean 0 and variance d minus s identity. And so they obtained the exact Ito-Wiener expansion, and through estimation of the L2 norm of each term here, of this Ito-Wiener expansion, they came to prove that we can find the renormalization that were proposed before by just estimating the L2 norm of each term here. It happens that even in dimension greater or equal than 4, a similar result can be obtained. Of course, now the density rho 2 does not exist, but we can define it by the second approach. We can define it as a limit of approximation of the delta zero function. In fact, the limit when epsilon goes to 0 of this integral, the epsilon d wt minus ws minus u exists, but in every Sobolev space d2 gamma, for gamma strictly smaller than 4 minus d over 2. Of course, here d is greater or equal than 4, and this 4 minus d over 2 is less or equal than 0. So this limit exists in every Sobolev space with this condition. So gamma here is strictly negative, and this limit is so no more a random variable, but a generalized Wiener function. And we have its Ito-Wiener expansion, but of course this Ito-Wiener expansion does not converge in L2 sense. We have to multiply each term here by some power of k plus 1. Let me just recall the construction of these Sobolev spaces. In fact, D2 gamma is the completion of the following space. We just take the square integrable random variable, which is measurable with respect to the Wiener process, and which consists of a finite sum of their Ito-Wiener expansion contains only a finite sum. Or we can just call them polynomials. So this subspace of L2 is a dense subspace, and we just need to take the completion with respect to the following norm. We multiply the L2 norm of each term of the Ito-Wiener expansion by k plus 1 to the power gamma. When gamma is strictly positive, we have smaller subspaces of L2, and for negative gamma, we have some bigger spaces. And of course, here when the index is negative, the elements here are called generalized Wiener function or generalized Gaussian function. So here, this row 2 of U now is constructed in every dimension. In dimension 2 or 3, it is obtained as a density of the vegetation measure. And in dimension greater or equal than 4, it is a generalized Wiener function, and we have its Ito-Wiener expansion. In dimension 2 and 3, we have seen that it blows up at the origin, and this property, that the existence of this singularity at the point 0, this peak at the point 0, that is what we call intermittency. In fact, intermittency is first, oh, I'm very sorry. Intermittency first appeared in a paper written by Zeldovich, Molchanov, Rozmaikin, and Sokolov, called Intermittency Around the Media. And it is a paper about thermodynamics. And this phenomena of intermittency appeared in some thermodynamic aspects, especially when it appears some rare but high peaks in the behavior of some random quantity. We can even read from the paper some specific structure in which a growing quantity reaches record high values, typically arise for instabilities in a random media. And despite the rarity of this concentration, they dominate the integral characteristics of the growing quantity, the mean value, the mean square value. The appearance of such structures is called intermittency. And this intermittency now has been studied for the double intersection local time. It has been studied through L2 means, through estimation of the L2 norm. And we want to, in fact, to obtain a more specific estimation, and precisely we want to obtain some pathwise description of the situation around the origin. How does each term of the Ito-Wiener expansion blows up? How does it behave when u with this the space variable u goes to 0? So we will consider again this Ito-Wiener expansion obtained, but we will think about each term in a pathwise way. For this, if we look again into these terms of the Ito-Wiener expansion, these are mainly integrals over time, the SDT. We have a product of Hermite polynomials from the Wiener increments, from the Brownian motion increments, and we have some polynomials from the spatial variable u and divided by t minus s. So we begin by the following estimation. For every u in Rd, d greater or equal than 2, we have the following estimate for this integral. The integral over delta 2, 1 minus 1 over t minus s to the power theta. And here this Gaussian density p t minus s d on u ds dt, it is equivalent to, when u goes to 0, to some constant here with which we can precise exactly, described by the gamma function, over the norm of u to the power 2 theta plus t minus 2. This when theta is strictly greater than 1 minus the dimension over 2. In the case when theta is equal to 1 minus the dimension over 2, some logarithm here will appear with some constant. Another estimation also. Oh, I'm very sorry. I think that I opened the wrong file, but the next estimate is if we consider the one-dimensional Brownian motion, then almost surely Hermite polynomials from wt minus ws divided by the square root of t minus s is less or equal than some constant here, factorial of n square root of e divided by t minus s to the power n over 2. And here we have exponent of absolute value of wt minus w of s. And we have here a sketch. Oh. I'm sorry, can I open a new file, please?
Okay.
I'm very sorry. we are again. I'm very sorry, please. So if we take Hermite polynomials from the increments of Brownian motion divided by square root of t minus s, it is divided by some constant, less or equal than some constant here, divided by t minus s to the power n over 2 exponent of wt minus ws. An idea of the proof is the following. We consider the generating function of the Hermite polynomials. So exponent of z wt minus ws minus z square over 2t minus s. We know this is equal to the sum from 0 to infinity. Here t minus s to the power n over 2 Hermite polynomial from wt minus ws divided by the square root of t minus s. And here we add z to the power n. This is for any complex number z. Of course, then from this expression, we can see that this t minus s to the power n over 2 by this function from the increments is just the n derivative of this function at the point 0. And as this is clearly analytic function, this nth derivative at the point 0 can be obtained through the Cauchy formula. Here we just need to integrate over the unit circle, the set of complex numbers with modulus equal to 1. And to obtain the estimation with absolute value, we just need an estimation of the modulus of this analytic function for each complex number of modulus 1, and we can check that this modulus is less or equal than some constant times the expectation of absolute value of wt minus ws. We recall also an interesting estimates from Shigo about Hermite polynomials. If alpha is between 1 over 4 and 1/2, then there exists a constant c which is uniform in n and x, n integer and x and real number, such that absolute value of hn of x exponent of minus alpha x squared is less or equal than c, and then the square root of n factorial n to the power minus 8 alpha minus 1 divided by 12. This is also a useful estimate, and using these old and new estimates, we obtain this following main result. If we denote by zi the maximum of wi of s, I recall that the Brownian motion here is w1, w2, w. These are the components of the Brownian motion. Then we have the almost sure estimate when u goes to 0, when the point u from ID goes to 0. So the absolute value of this integral that appears in the Ito-Wiener expansion of rho 2 is less or equal than some constant times the logarithm of 1 over the norm of u. This when the dimension is equal to 2, and just for the very first term of the Ito-Wiener expansion, we have this logarithm. And for other terms in dimension 2 or any other term in dimension greater or equal than 3, we have some constant, and we have here exponent of here these maximums, and divided by some power of the norm of u. The power is n1 plus nd, the sum of these integers here, and plus the dimension t minus 2. And this is so quite new estimates that describes the behavior of the almost sure behavior of these integrals when u goes to 0. Also, we propose, we are planning to see what happens with the case of d greater or equal than 4, we have said that the root 2, in this case, root 2 of u is no more a random variable, but a generalized Wiener function. But we know that from this theorem of Sujita, 1987, that if we consider the classical Wiener space W0D, which consists of all continuous function from 0, 1 to Rd, which vanish at the point 0, equipped with its Borel sigma field and the standard Wiener measure. If a generalized Wiener function is positive, which means that whenever tested against positive test function, it is positive, then it can be expressed by a unique finite positive measure on this Wiener space. So this representation of positive generalized Wiener function by positive finite measures allow us to express our root 2 of u in dimension greater or equal than 4 in terms of positive measures, positive finite measures. In fact, from this definition of root 2, we can see that it is a limit of positive Wiener function, and so it is a positive generalized Wiener function. Consequently, by the theorem of Sujita, there exists a unique finite positive measure, theta u, such that the canonical dual pairing between root 2 and any test function here will be just the integral of f with respect to this positive measure. Of course, we are planning, or we want to understand the intermittency phenomena for root 2 through this positive measure theta u. How does this singularity at the point 0, how is it described through this positive measure? So this is our plan for the future work, and now I just want to say thank you for your attention.
Okay, thank you very much. Despite of this black polygonal lines which appears on your slides, you know, it remained me Brownian motion. So maybe it was just preparing to show us some picture of Brownian motion, but it is okay. And now maybe somebody have questions or comments, please.
So may I ask a stupid question? Could the speaker again explain what is intermittency in this particular case? Because I have got the general definition of intermittency, but which intermittency you are dealing with?
The intermittency here is the fact that we have a divergent behavior at the point 0. We have this row 2 of u here in dimension 2 and 3. In fact, it is continuous everywhere in Rd, but at the point 0, in fact, it blows up. It goes to infinity. So we are we are facing a peak, some high value at some specific point, and that's exactly the intermittency here. Okay.
Okay. Thank you.
Yeah. Thank you.
Okay. Some other questions, please. Okay, if there are no other questions, let me know that it will be really very interesting to understand the behavior of the generalized functionals related to not a poor self-intersection density, but its formal expression in the higher dimension. Because we know that this generalized functional exists, and we hope that using obtained estimation on the elements of Ito-Wiener expansion, we will say something about these measures theta u, because they are singular to the Wiener measure, but concentrated on some small set of positive capacity on the Wiener in the Wiener space. So we will see what happened with these measures when u tends to 0, and we supposed to say something about the structure of these measures. From this point of view, it seems to me that this is interesting direction of investigation, and I hope that next time Noël will discuss something interesting in this case.
I hope to.
Okay, if there are no other comments, questions, then we finish our work for today, and